together. The other thing is what we call intercooling. Intercooling is that this is the inlet to the compressor, and then we do not do the compression all the way in one compressor, but we compress it for a certain pressure, and then cool it again, and then compress it in another compressor. So what we do, this is what we call intercooling. This is supposed to be one compressor. All of this is one compressor. Now we divide it to two compressors, stage 1 and stage 2. And in between we do intercooling. Let me go to the next slide and then we'll show what happens here. So this is the intercooling. What do we mean by intercooling? Intercooling, this is the compression process. This is supposed to be without intercooling. And remember, on the PV diagram, then we have the work is integral of VTP. So we have injected on this axis here. So this is integral of VTP for the compressor. To get the work for the compressor, it is minus integral of VTP, and therefore it is the area under the figure on the PV on the P axis. So this is the work done here. So now we have from 1 to 2 prime. If this goes to one step to one compression step, then what we do in intercooling is this. At this stage here, which is C, we take it out of the compressor and we cool it. Cool it means that this is constant temperature, and therefore we have this is here. Cool it means that we take heat out of it, but at constant pressure. So it's a constant pressure process, but it's cool. Therefore, it goes to this point here, D. It is a cooled temperature, and then we compress again. So this is a compression from D to 2. This is in the second compressor. From 1 to C, this is the first compressor. What is the result here is that the area under this here, which is this area, now is smaller by this area. So we have actually reduced the amount of work by this amount here. And therefore I can say here, this is, of course, both of them are isentropic, and therefore this is the objective of intercooling is to reduce the compressor work. I'll come again and explain it. So this goes like that. So this goes in the first compressor, then it goes here into cooling process, and then it is compressed again in the second compressor. Okay. So this is the process again here. This is compression in the first stage, then we cool it. So this will be constant pressure cooling in the intercooler. And then it is compressed again to the inlet to the combustion chamber. Okay, so this is the idea of intercooling. Okay. Now let us see here. So this is the area. You see, this is the area here, which is under this is with intercooling. So this is the work done with intercooling. The work done without intercooling, this is the amount here. So the saving here is the amount. We save this amount here. So let me say again, this is the process. Now we have this is the area with intercooling, and then this is the area without intercooling. And therefore means that we have saved this amount of work for the compression. And remember here, this is important here. It was not important in the pump. We did not do this in chapter 8. Why? Because the compression work, which is the pump, was very negligible. But here, as you remember, that compressor work is 40% of the turbine work, and therefore this is very important here. It saves a lot of work. Now let us combine. Let us go to this on the TS diagram. On the TS diagram, so let us understand the process in TS diagram. This is the compression process. This was supposed to be compression process going to the combustion chamber, expansion of the turbine, and this is what we call the Brayton cycle. The change is done here. We compress not to the combustion chamber pressure, not to the inlet to the turbine pressure, but this is here is up to a certain part here. Then we cool it, and then we compress it again here. All right. So this saves this amount of work that's done here. Also, we can see here that the compression here is at a lower temperature, and therefore we can, when this here becomes constant, means that we are reducing TL in this, we are reducing TL in this case, and therefore we have the work will be less. Okay, so now this is the third change, which is intercooling. Let us look at the whole thing now. So now this is the conclusion of all of modification. Okay, this is a simple cycle. Okay, the Brayton cycle is a simple cycle. You have the air comes compressed, then goes to the heat exchanger or the burner, the combustor, and then to the turbine. So this is a simple cycle. Okay, and we know how to solve that. Normally we are given P1 and T1 here. Then we are given the compression ratio. So we'll go to state 2. Then we have state 3 is given, so we can calculate Qn. Then we have from 3 to 4 expansion and calculate T4 and get the turbine work minus the compressor work. This will be W net, and then divide by Qn. This will give us the efficiency. Now let us look at all of the modifications here. So where is this cycle? Simple cycle. Simple cycle is here. If I go to the compression, go to the combustor and the turbine. So this was a simple cycle. Compressor, combustor, turbine. Okay, so this is a simple cycle here, which is, if I remove all the other parts, if I remove this part and all reheat, intercooling, so I have one compressor, the air comes from atmosphere, then it is compressed, goes to the combustion chamber, goes to the turbine. This is a simple cycle. Now let us see what modification we have done. The first modification here is we have, this is the inlet now. We have two compressors instead of one. And in the middle here, we have intercooling. So the air comes here, compressed, intercooled, and then go to the second compressor. So this is the process here. So this is now, this is, if you go vertical like that, this would be the one compressor. But now the process here is that we have one, compressed to 2, cooled to 3, then compressed to 4. So this is now 4 is the exit of the compressor here, which is all of this now. So instead of one compressor, we added another compressor with intercooling. Then it goes from R4, and then we have, this is the regenerator here. We take the exit from the last turbine, and then we use it here for heating the air before it goes to the combustor. So this is what we have here from 4 to 5. The air temperature has increased in this process from 4 to 5. Then it goes to the combustion chamber here, and then in the expansion process also we used to have one turbine. Here we are going to have two turbines. One turbine, then reheat, and another turbine. So one turbine, expansion, reheat, and another turbine. And then the gases out of that will go to the regenerator, go to the atmosphere. So this is now is a cycle with all modifications that we have and that we want to do. Of course, this cycle will have more power. Why? Because we have this amount of power increased due to reheat, and less power in the compressor because this is for intercooling. So we expect now that W turbine is higher, W compressor is less, so W net has been increased. The second part here is the efficiency. Instead of going to the combustor at state 4, now we'll go at state 5, and therefore the heat addition, both of these heat addition here will be less than what's required for the simple cycle. So it means that we have improved the efficiency, and the reason for improving the efficiency is the regenerator. Then we increase the power by considering reheat and intercooling. And that's it for this cycle. I want just now to see how we calculate for this cycle. Before I go here, let me start thinking with you here. How do you calculate the output of this cycle? So what we need to do here is to go find all the temperature, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So these are all the temperatures that we are looking for here. And let me go and see here how to calculate W turbine. So W turbine, I have, this is here W turbine 1, so 6 minus 7 and 8 minus 9. But because of this is irreversible, so I have to say here eta turbine 6 minus 7s plus eta turbine 2, 8 minus 9s. So this will give me W turbine, which is this expansion here, this 2 expansion. Then we have W compression is 1 minus 2, 2 minus 1, and then plus 4 minus 3. So now we say here, because of eta compressor, so it will be eta compressor 1 divided by H2 minus HS, which is as product, divided by eta compressor 1, plus 4S minus 3 over divided by H, by the efficiency of compressor 2. Then we have the heat addition. So now I have heat addition is, where is heat addition? I have 8 minus 7. This is 1 heat addition is the heat, and the main heat addition is 6 minus 5. So 6 minus 5 plus 8 minus 7, this will give you QN. Then, of course, we have eta regenerator. So now H5 minus H4, this is the actual increase in the regenerator, and divided here by, in this case, this is the exit here from the turbine. This is the one used to heat that. So now we have the maximum here I can reach is H9. So this will be over H9 minus H4. So this will give us the regeneration efficiency. Let us solve a problem now. I ask you here, calculate the efficiency of the cycle, which is W net over QH. So you need to calculate QH, W net, and you need to calculate QN. So now if I go back here, then this is the question here, calculate W turbine, W compressor. So now what do you want from me? You want certain amount of data, right? So the data is, how do you present all of this cycle? So of course, first you have to set the point 1. Point 1 is P1 and T1, normally this is atmospheric. So you want from me pressure P1 and T1. So this is given, it has to be given the problem. If not given, then we assume there are atmospheric conditions. So now we have fixed state 1. Then I know I'm going to move in this line here. But to move in this line, I have to move isentropic. So I go isentropic and get T2S. How I get T2S? We apply the equation 2 to S over T1 is equal to P2S over P1 to the K minus 1 over K. Therefore, in the problem, we have to give you here this pressure. Once you get this, now we give you also efficiency. So you can get H2. So now we go from 1 to 1 to 2S isentropically. So I give you the pressure of P2S. Then you get T2S. Then you divide by the efficiency to get state 2. So now we have state 1 is fixed, state 2 is fixed. Means that I have T1 and I have T2. Okay. Once I have T1 and T2, then I can say that this is Cp T2 minus T1. So I can calculate this part from the compression work. Then we have cooling here. So we'll cool this here. So we'll go out along constant pressure. So I do not need any data here. But he has to tell me where to stop here. So this is stop here at state 3. So now the problem will tell me T3 is given. So once I get T3, I have the pressure here, so I fix state 3. Then I go do the same here, go isentropically up till this pressure. So this pressure will be given in the problem. So now I have 4S. Then the efficiency will be given, so I divide here, I get T4. So now I have 4 and 3, therefore I can say Cp T4 minus T3, and then I calculate the compression work, all of it now. Then we'll go to the turbine. Normally state 6 will be given here. Pressure T3 also will be given because this will sit as 1100, 1200 Kelvin, something like that. This will be given the problem. So, and I have the pressure here given, so I can fix state 6. 6 will go to state 7S. Isentropically and then multiply by the efficiency to get 7. So now this pressure will be given to you here. Okay. Then once I get 6 and 7, then I can get the work, the Cp delta T here. Then, so this pressure will be given, then this temperature also will be given to you. So it is how to know that you need this temperature or not. It is how to proceed. I know I know the direction here, but where to stop here, he has to give me the pressure. Then I know the pressure here. Where to stop here, he has to give me the temperature. So now I have T8, then I have expansion here. This is P1 is the same as inlet, therefore I can define 8 and 9. So with this here we can calculate W turbine. Then we'll go now to Qn. So to get Q, then I have to say that this is here. This part, خلاص, I can say 8 minus 7. This is in the part of heat addition. This is the reheat. This is calculate now. But in the first combustor, I need state 5. Therefore, we need here the efficiency of the regenerator. So this should be given now. With this given, I have T8, T9, H9. I have H4. And then I have H4, so I can calculate from this here, I can calculate H9. Now I have, H5. So now I have H5 to 6 is given here, and 8 to 7 to 8 is given here, so I can calculate Qn. Then by dividing here W net over Qn, then I can calculate the efficiency. The concept is there. I mean, the same concept with the simple cycle. As you go from here to there and to here, this is a simple cycle. You just follow the same procedure, but we have many parts to solve other than for the simple cycle. But the procedure is the same. And just you have more terms than before. All right. Okay. So this is here ends the part for gas turbine, which is the main part for chapter 9. Any question you have? Anything is not understood here? And if I give you a problem now with the data, P1, T1, I give you the pressure here, I give you the temperature here, I give you the pressure, and then I give you the efficiency of regenerator, give you the temperature here, and then this pressure, this temperature, then you should be able to calculate all the temperatures and come up with this here. Any question regarding this?
دكتور P9 نفسها P1 يا دكتور؟
T9 is not the same as T1, no.
pressure.
The pressure is the same as P1 because we neglect the pressure losses here. Yeah, we neglect the. Let us look at this here. Let us look at the diagram here. This is the diagram here. Where are the pressure change? Okay. Now, of course, in the compressors, the pressure changes. This is definitely there. Here we have pressure loss. But of course, we neglect that. From 2 to 3, we say that the pressure is constant here. This is an approximation. And we are not going to consider pressure loss here in thermodynamics too. We leave it to another course. But this is here, there's some pressure loss, but this can be neglected. Then we have a pressure increase here in the second compressor. Then this goes here to heat exchanger. So this is just a flow in a pipe here. There's some pressure losses, but we can neglect that. Then it goes to the combustor here. Also, there's some pressure losses, but we can neglect that. And therefore, 4, 5, and 6 are the same pressure. 4, 5, and 6, same pressure. Then we have, this goes to turbine. Of course, there's a loss in the pressure. Then it goes to the combustor too. This is piping system here, and therefore there's pressure loss that we can neglect. Then it goes to the turbine, and then out of the turbine at 9. It goes from 9 here to the atmospheric pressure again. So now this is here. So this is the atmospheric pressure, and therefore this pressure from 9, 10, and 1, these are the same pressure. There's some pressure losses here, yes, but we neglect this. So 9 and 1 are the same pressure. So P9 is actually given as far as P1 is given. You can consider them the same. So now in this here, this is constant pressure, approximation. This is constant pressure, approximation. This is constant pressure. This is constant pressure. This is constant pressure. All right, answered?
Yes, doctor.
Okay, any other questions? It's very good to ask now. Very good questions, yes. Because we will not give you P9. So I'll give you P1, but because of this here, you assume that P9 is the same as P1. Okay, so this is done with the reheat, regeneration, intercooling. This is all the modifications that we can do with this cycle. Now we'll go to another application here, which is very, very important application, which is known as compained gas turbine vapor power cycle. I know that you have already solved what's called binary cycle as one example there, and this is considering two components together, two cycles together. Here combined says combined gas turbine. So I have a gas turbine and vapor power cycle. This is, what is this here? This is a gas turbine. So it's compressor, combustor, and turbine. If you look at this here, this is a pump, boiler, turbine, and condenser. So this is chapter 8, Rankine cycle, and this is chapter 9 is gas turbine cycle. What do you want to do here? As we described earlier, the temperature at the exit of the turbine here is high. It goes to 450 degrees centigrade, means that 700 degree Kelvin. And for this simple cycle here, we throw this energy to the atmosphere, and we lose all the exergy in that air. And therefore, we used it before in the regeneration cycle to heat the air before it goes to the combustor. But this was not sufficient. It improves the efficiency, but it was not sufficient, particularly if we have large amount of flow in this simple cycle. So what do we do now? We have a lot of energy in this form here. We utilize this energy to heat the water in the Rankine cycle. Remember that we have a pump, we have a boiler, turbine, steam turbine, and a condenser. Now we are going to have this as a heat exchanger. And where do we get the heat from? We want to boil the water here. We take this here and use it for heating the water, boiling the water, and then this will run as the boiler for. So the energy exit from this is the energy out here, will be used for as heat added in the boiler of the gas of the steam turbine cycle. So let me say this again here. This is a gas turbine. We found here that there is a lot of energy here that we can use, and therefore we are using this energy, which is 4 minus 5, to boil the water in the Rankine cycle. So now we have a Rankine cycle, and the heat will not be coming from fuel, will come from the energy out of that. So with this here, we have generated power here at no cost. We do not have any extra cost here. Previously, we have only steam turbine, gas turbine here, so the power from the turbine comes here. Now we added Rankine cycle and we get more power here. So this is an extra power now, and at no cost. Why? Because we get the heat here, the energy from the gases from the gas turbine. According to this, what we call it here, it is a boiler, right? This is a boiler or steam generator for the point of view of the Rankine cycle. So this is here is what we call heat recovery steam generator. This is how it is known in industry. Heat recovery. Where is this heat? This is the heat here. This is the energy that was lost. We call it heat recovery because we recover this heat. We recover this heat. In what? In a steam generator. In a steam generation. So this is here is called heat recovery steam generator. Sometimes we call it also waste heat. This is waste heat recovery boiler because we recover this waste heat. So this was waste heat. It was supposed to go to the atmosphere, and therefore we utilize this in steam generation here, and therefore we have this is 4 to 5. This is to steam generation. So now we add it here instead of having simple cycle. Now we have what we call compained gas turbine vapor power cycle. So this is a combination here, and this is what we call compained vapor power cycle. And then we have this in Rabel. I had one student, I think it was Ali Busaleh, I believe. He was with me in the office hour, and I asked him, where is Rabel? He didn't know that. Do you know where is Rabel or not?
At the western coast.
On the Red Sea, I believe, right?
Yes, the western coast.
Okay. A long time ago, they have this cycle there. It is already available in Rabel, and currently many of the gas turbines, this is what we call simple gas turbine in the kingdom here. From now on, they do not do any, they do not have any gas turbine cycle. They have what we call compained cycle. They make both of them. Why? Because now let us look at the efficiency of this here if you want to use only simple cycle. In simple cycle, the efficiency is 28%. Do you know what the efficiency of this here? Is 55%. So now we moved from about 30%, we added 25%, because we have now turbine work at no cost. And therefore the net power output now is W gas turbine. You calculate this from H3 minus H4 minus H2 minus H1. So this will give you gas turbine as we solve it in chapter 9. Then we have W steam or W vapor. This is from the turbine. So now I add these together and I divide them by Qn. It is the same Qn as that. So previously for the gas turbine, I have this one over this gives me the efficiency, which is 30%. Now with the combined cycle, I have this plus this over the same Qn. And therefore the efficiency moves from 30% to 55%. So definitely it works to do that. And from now on, there will be no gas turbine, simple gas turbine cycle, and there will be something like combined cycle. But why did we use this in the past? Because you know, if you have your village, you do not have electricity, you can fix gas turbine cycle in less than 9 months. So this is very fast to do. But to do this, you need at least 2 years to build that. But now we have a large amount of electricity, so you can supply any university to any village until you build this plant here. So this is what's known as combined gas turbine cycle. I put both of them here. This is the simple cycle, which is the gas turbine, and this is the Rankine cycle, simple Rankine cycle. What we have done is we have joined these together here. How did we join this together? This is the output from here. We take it to as a heat in the boiler here. So the way to calculate this is the same as simple cycle. You have a simple cycle, you will be given P1 and T1, you will be given the compression ratio, calculate T2, T3 will be given, you calculate T4, and therefore you can calculate W turbine, W compressor, and then you calculate W turbine, W net for the gas turbine. The same here for the cycle. Then you will be given 3, then you move to 4, then you will be given 1 prime here. You calculate W turbine, you calculate W pump, and therefore you get W turbine here for the turbine. For that, then you add W gas and W vapor over Qn. Then you solve the problem. So this is what's known as the combined cycle, and what we added here is what's called heat recovery steam generator. So you solve this as normal as you have. You solve this as we have in chapter 9 and chapter 8. And then the only thing that's new here is that how do you link the two cycles together? And this is done here in the heat recovery steam generator or waste heat recovery boiler. And this is what we see here. We just make an energy balance here. Okay. Can anyone make an energy balance for this? I need a volunteer.
Yes, Doctor.
Yes, please go ahead.
H4,
yes.
H5 minus H4.
Okay. H4 minus H5 because 4 is greater than 5.
Yes. H4 okay. Minus H5 equal H7 minus H6.
Remember one thing, okay? Is that correct?
No.
Flow rate.
Flow rate, very good. Because they are not the same flow rate. So you have to say the mass of gases multiplied by H4 minus H5 equals the mass of steam multiplied by H7 minus H6. Then it is correct. We have to go to the original equation. The original equation says sigma mi hi equal to sigma. There is a mass there. If the mass is the same, then fine. But the mass here is definitely not the same. The mass of gases here is the same. So what do we do with this here? As a matter of fact, when I calculate W here, I have to say the mass of gases H3 minus H4. I have to get this in kilowatt. I cannot calculate it per kilogram. When I add it to this, then it has to be in megawatt, both of them. So now what I say here is this is used to get the mass flow rate of the vapor with respect to the gas. So the problem will tell you that. Will tell you the properties of the such that you can solve the cycle, and it will give you the mass of the air here. Then based on this here, you calculate the mass of the steam, and therefore you calculate this is W turbine, W turbine here, multiply by M dot, you get that work, So this is here the energy balance that our colleague here have got it, two colleagues as a matter of fact, and then is used to calculate the mass of the vapor. We will not give you the mass of the vapor, we'll give you only this mass, and then from the mass of vapor, you get the mass of vapor, and then you calculate that. Okay. So now let me say here, let me continue with this. Okay, this one. Okay. So now we say here eta is equal to W dot gases. You cannot add here delta H is the ensalpes here, H3 minus H4 minus H2 minus H1. You cannot do that. You have to multiply by M dot. So you get this in megawatt, and you get this in megawatt. Then you divide this by on megawatt here. Then this is the equation used here, which you just mentioned now, is that to get the mass of vapor from this equation. So the problem will be like that. We'll give you state 1, state 2. State 1, the pressure ratio, temperature T3, and therefore you can solve this cycle here. Then we will give you the temperature T5 here, what's the value for that, and therefore, based on the calculation of this also, you calculate the mass flow rate of the gas. Then you calculate per kilogram here, W net, multiplied by the mass, you get W dot gas. Then calculate the W net here, multiplied by M vapor, get that here. How to get M vapor? Then we will give you only in the problem M dot gas. Then you use this equation to calculate M dot vapor. Then from M dot vapor, you can calculate W vapor. Then you divide by Qn. Qn here is M dot gases multiplied by H3 minus H2. Then you get the efficiency, and you expect that this efficiency is around 50-something%. And this is the advantage of the compained cycle. All right, Shabab? Any question about this? Questions? Is it clear? Shabab, are you still with me, huh?
Clear, Doctor.
Yes.
Okay. So this cycle
Yes,
is
clear.
it's important. I know you complained about the binary cycle, but this is a real cycle which is binary here. It was similar to this here, but this was ammonia and this was, I think it was gas. So this is always we want to use the temperature here to solve that. So you can have Rankine cycle here, but this is well known combined gas turbine cycle, and it is in Korea now. We have one plant in Korea for gas turbine, combined gas turbine, and it will be available everywhere in the kingdom very soon because you change the efficiency here from 30% to around 55%, and this is why it works now for saving energy and so on. Okay, so now this is the cycle here, and sometimes also we link it here to what we say combined district heating. Is that what we have here is we use this as cogeneration now. With this here cycle, we can also add cogeneration. Cogeneration here means that I want to have and produce electricity, the power here, and then also you produce heat from that. So now this is a cogeneration combined cycle. So this is used for producing work, and then also for producing heat to heating or to drying, as you mentioned in some other applications. You need steam to get it here for heating a building or a hospital or something like that. So this is what we call here combined cycle cogeneration plant. Combined cycle because it has the gas turbine combined with the Rankine cycle, with the steam power plant. And then cogeneration because it produces heat and work. So it produces energy, electrical energy, and also so you can, this is a village here, you have electricity coming to that. He's presenting this with pulse here, it's nice. And then you have heating inside of that, so you do not have to use air conditioning because air conditioning is so expensive. It takes the electrical energy. The electrical energy is the high cost energy. heat is low cost, and therefore it is not recommended to use a heater, for example, use electricity to heat the building. This is not recommended, but what is recommended here is that you use heat to use that. So we use steam, we use heat to heat the building, and we use the electrical energy to have light in the building. So this is what we call compained gas turbine, vapor power cycle, cogeneration plant. This is compained cycle, gives you more power. With cogeneration means that you produce steam also. This is both of this here. All right. Okay, so this is the compained cycle, and this we conclude now the gas turbine part. But all of this here, it happens on the ground here. We mentioned that the gas turbine is used in stationary to produce power and in aircrafts. So now we cover the part for stationary gas turbine, how it is used on the ground here. These are being simple cycle, compained cogeneration cycle, or now we can use it as gas turbine for aircraft. So this is the last part for this chapter, which is gas turbine for aircraft propulsion. Let me just go for this in 5 minutes or so to explain the physics beyond that. This is here what you see in the wing of an airplane. I know that this is not available much these days, but this is what's happening for aircrafts. You have the air goes in, it goes to a compressor, combustion chamber, and a turbine. So this is the main part for gas turbine. This is a gas turbine here. Okay, but the purpose in the stationary gas turbine is that the turbine produces work, runs the compressor, and then we connect this to a generator to give us electricity. This is on the stationary gas turbine. Of course, when you are flying, you do not produce electricity. But what you need here is to have high velocity to push the plane in this direction. So now we have the air, it goes to the compressor, then to the combustion chamber, to the turbine. The turbine, it will expand partially in the turbine just to run the compressor. So I need only 40% here. So I expand in the turbine, only 40% of expansion to feed the compressor. Then I still have a high enthalpy here for the gases. These gases will expand in a nozzle, and this nozzle will give you high velocity here that pushes the plane in this direction. Is that clear, Shabab? Are you aware of that? So when you go to the wing now, when you are going, particularly if you are going in a first class or horizon, then you will see in the wing there, or if you are staying on the ground, then you will see here this entrance here. So this is in the wing here. The wing is like this here, and then we have this is in the wing. The air comes here. Then this is a gas turbine there, and the air comes. The gases come out here, pushing the plane in this direction. All right. Two things that's different from the previous slide. This is the same compressor, combustor, and turbine. So we deal with them exactly. So it's 1 to 2. How do you get this? You solve them. You have state 1 to go to state 2 isentropically. From 2 to 3, you have temperature T3 is given, and then you go to the turbine from 3 to 4. This is a simple gas turbine. In the gas turbine for aircraft, we add two things here. This is very important. This is a nozzle here. We have to have a nozzle here because the nozzle will give you the high velocity. This is the exit of the plane. Then we add another part here which is called diffuser. Why add this part? Remember here that this plane is moving in this direction. Means that this is the stagnant air. When the aircraft moves in this direction, then the air comes. If you are sitting here, you will find that the air is coming at this speed here to the compressor, and therefore we utilize this energy. So now I have high velocity. I change it to pressure such that I can have at pressure state 1 here higher pressure than what I have in that. Just I will explain this again when we go to the test diagram, but this is the two things that we add here. From 1 to 4, this is the same as gas turbine. So when I ask you to solve this part, if you know 1, you can calculate everything up to 1, you can calculate to 2, you can calculate to 4, everything as a gas turbine. But now we added two parts, diffuser and the nozzle. The nozzle, it changes the enthalpy to kinetic energy to have high velocity. The diffuser is the opposite to that. It changes the kinetic energy to pressure. So now the pressure increases from A to 1. So if this is atmospheric, we increase the pressure to 1 here. So it goes to a compressor at a higher pressure than the atmosphere. And this saves energy done by the required by the compressor. And then, so this is the diffuser. In the nozzle, the pressure decreases and the velocity increases. And you know why the velocity here, we get this velocity. Okay, and of course, you can expect here that the velocity is high, and the changes in kinetic energy is the only location that we cannot neglect the kinetic energy. This is the only location we cannot neglect the kinetic. In all previous parts, we say neglect changes in kinetic energy. Neglected changes in kinetic energy. Kinetic energy changes are neglected. Only in this part here, you cannot neglect the kinetic energy. I may ask you, what's V5? The question comes here, calculate, this is the objective here of this cycle. Calculate this, when I give you a problem here, what's the question? Will I ask you calculate the turbine work? Will I ask you calculate the net power?
No.
Of course not. I mean, you are not interested in that. Am I going to ask you about the efficiency? I know it's important, but on the air,
No.
you are only interested in security. You want to be safe, right? You do not want. You want to go fast. You never say about. You pay more. You pay more, but not more because of the efficiency. You pay more because of you want to go fast, and therefore this velocity is high. If I ask you what's the velocity of your car, when you go from here to Riyadh or something, what's the velocity you use?
120 kilometers.
100 kilometers per hour. Can I just ask you how much this you have in meter per second?
Multiply by million. I think.
Multiply by 1,000 to change it to meter, divide by 3,600. So you divide by 3.6. So let us say divide by 3. So the meter, it is meter per second is 30 meter per second, around 40. I know you go more than 120, so let us say 40 meter per second, all right, or even 50 meter per second. So it is 2 digits, right? You never go to 3 digits, huh? You never go to 100 meter per second, 100 meter per second, which means 360 kilometer per hour. You do not go to that. So now, what is the velocity here? In kilometer per hour, right? Approximately.
1,000.
1,000 kilometer per hour. So you go to 1,000 divided by 3 to make it meter per second. So how much now? Around 300 meter per second. So it is 3 digits, right?
Yes.
Yes.
Okay, so I want to concentrate on that. If you make a mistake here and get these 2 digits, and then you pay millions of dollars for this, they will send you a car. All right, because you have, this is here 2 digits, means that this is the velocity of the car. So the question here in this chapter is calculate this velocity. And I don't want you to do any mistake in that. If it comes to digits, then you have done a mistake. And officially, if you send it to an industry outside, and then you calculate this as 40 meter per second, you want 40 meter per second, they will send you a nice car, and this is done the job. So remember here that the velocity of your car is 2 digits, 30 meter per second or so. Here, this is 3 digits, 300 meter per second or so. So if you get these 2 digits, means that you have done a big mistake. All right. So we will come to this later on. So this is just an introductory here, again, I want some animations for now gas turbine for aircraft propulsion. So I need 4 or 5 of you to send some animations on this. Hassan, are you counting you did not send me the names of the students. Also, I want to say one note here. When you send me WhatsApp, you send me your number there, but I need your name. When you send us WhatsApp, please mention the names there because I cannot get that. Okay, I'll stop here. So I want you to read a little bit about gas turbine aircraft, understand what are the processes done in the aircraft, give me some animations, and then we will continue this in our next class, inshallah. All right. Any questions or any questions? The course, the exams, whatever. If there's no question in the class here, let me take attendance before I forget that. Let me take attendance.